This episode is brought to you by Fabulous. Imagine the day a civilization discovers the starry night sky above contains billions of worlds awaiting their arrival. Now imagine the day they realize those voyages will never be made. So earlier this week we were talking about Kessler Syndrome, collision cascades around planets that might make spaceflight very dangerous or even impossible, and it is one of many things that might make it very hard for them to leave their world to colonize space, or potentially even be able to contemplate the possibility. Some of these might be natural causes, some might be self-inflicted or even from exterior sources, like an older alien civilization quarantining a planet. Now, when we discuss the Fermi paradox, the big question of where all the aliens are, we often emphasize that many solutions don't work simply because we wouldn't expect them to be universal. We call this non-exclusivity, as the idea that while we would expect the ability to build spaceships to be a trait exclusive to species with a knowledge of basic mathematics and physics, we would not expect the ability to go into space to be exclusive to, say, civilizations whose economic system was capitalist, communist, or socialist, given that the space race was between the USSR and USA. Space launches and the science and engineering for them have been achieved and improved by nations subscribing to all three approaches, so while it might be that one of these systems was better than others for colonizing space, we would say it was non-exclusive. Any are capable, though not necessarily equally capable. The same would apply to various religions or ideological beliefs, and of course to more mundane stuff like hair color or how many arms or heads a given alien had. Often with a Fermi paradox example, the proposed solution to the apparent paradox just doesn't hold up to scrutiny for non-exclusivity. We just wouldn't expect most planets life arose on to have thick dust clouds that obscure the sky, so that the inhabitants never even considered starflight, or some debris ring that made it a thing to contemplate but only as an expensive form of suicide. So while we will discuss the argument for some of our cases today, many are transparently not viable for a Fermi paradox solution, as they'd be exceptionally rare and with no clear link to inhabited worlds. And thus it is a pretty good topic for one of our Sci-Fi Sunday episodes too, as while each suggestion will be a situation that could plausibly come about, they are probably more of interest as plots for sci-fi novels than approaches for SETI, the search for extraterrestrial intelligence. As one such example, there are vast empty regions of the universe called cosmic voids. And these spots are not empty of matter, indeed they have stars and sometimes even galaxies in them, but they are a rare oasis in the desert, so to speak. In such a place, life might develop on a world around a star that was so far from any other star that they would have to get to late 20th century astronomical technology and infrastructure to even be aware there was a universe beyond their planet and sun. This is quite probably a case that's already happened if life is decently common enough, but it doesn't really matter to SETI because we are nowhere near any of those voids, and looking for our first example of intelligent life there would be like a person dumped in the middle of New York City trying to find an example of intelligent life and opting to leave the Atlantic seaboard entirely to hunt Antarctica on the off chance they found McMurdo or one of the other research stations there. There are vastly more galaxies to search near us than these voids are. This isn't universal though. We can make a decent case for Kessler Syndrome being very common or inevitable. As I said, we discussed that more earlier this week, and how civilizations might handle preventing or removing those cascade debris fields, but the basic concept works well for a Fermi paradox solution, especially given that we have only basic models of both those cascades and the solutions for managing them. They may be worse than expected and the solutions ineffective. So civilizations start exploring space and building up their orbital infrastructure, and eventually the amount of litter up there sets off the ruinous cascade we call Kessler Syndrome. The civilization, probably barely a century ahead of us in tech at best, likely does not have any off-world bases besides maybe their moon and some simple outposts on their equivalent of Mars or an asteroid mine. Space is already hard to build in, and now everything else they build costs even more to armor and has a shorter lifespan, and it just seems that the more they move into space, the more resistance they face, just getting into orbit and keeping a presence there. Such civilizations also have to worry about intentional cascades, nutcases or lesser powers who want to wreck things for those operating up there. Blowing up satellites and orbital infrastructure is vastly easier than building them, And the sad reality is that everyone who gets a successful foothold in space and nearby worlds, once exploited properly, becomes very powerful. Rival entities might feel this sort of asymmetric preemptive warfare was their only real chance to avoid being crushed later on. And there is an option for stealth. As an example, a submarine with an anti-satellite laser as a minor part of its armament and a secret part of its overall mission could be having its command staff firing that laser at a satellite every time it quietly surfaced in the ocean, unknown to most of its crew even. It would be very hard to prove anything happened. Now again, we discussed managing Kessler Syndrome last episode, and I can think of ways to manage that submarine case too. I would not even have suggested otherwise, but it is not hard to imagine ways in which Kessler Syndrome could become a major and unsolvable problem for civilizations, including its K2 version that changes us from debris orbiting Earth to debris orbiting the solar system in general. I would not call it a strong case as a Fermi paradox solution. However, we have to keep in mind that none of our Fermi paradox solutions really has an overwhelming case for it, and my assumption these days is that at least one major scientific concept we take for granted is wrong, or misunderstood so that we get a distorted view of the landscape. I have no idea which, mind you, or if it is any, but as an example, given that we do not have an orbital infrastructure right now, even though we would like to, and have spent hundreds of billions of dollars on space thus far, we do not want to rule out that all these problems facing us for developing space further do not have easy solutions that will make it practical and economically viable to colonize space. Kessler Syndrome might be one such example of that. Something like that could be self-perpetuating too. Planets can have naturally occurring rings. Nothing is really stopping a world like Earth from having ones as thick as Saturn's, but one theory for how such rings get maintained is by cryovolcanic eruptions of material from closer moons, and it is worth noting that many artificial processes might have a similar effect, pollution and smog equivalents from your orbital factories. We tend to assume once you get to space, things snowball out into the galaxy, but we might be jumping the gun on that. Sometime back in our episode looking at how space colonization could save Earth, I pointed out that not only would most interest in space colonization need to focus on how Earth benefited directly from it, but also that tons of our proposed benefits from space colonization are a bit hand-wavy. You don't really need to colonize the solar system, let alone the galaxy, to protect Earth from asteroids, for instance. You just need some big guns and tracking systems built in orbit. And with that case in mind, I ought to know that asteroids approaching spacefaring civilizations is not a crisis for them, it's a free economic boon, as they can just lasso it and use its material for building infrastructure. Something like that could produce a ton of orbital debris and pollution, but that doesn't necessarily mean they'd view that as a deal breaker. Sending out wave after wave of tiny and expendable robots to mine asteroids and bring the material back into the cloud for dropping down to Earth is a very viable approach. They might not care about a satellite grid then either, potentially using the cheap expendable robot eyes approach, or simply having improved storage for helium or hydrogen gas to replace their satellites with non-orbiting geostationary pods floating 100 kilometers up, protected from the debris by the atmosphere. We don't do that trick now because the tethers would be hard to make strong and the gas would leak through normal materials, but graphene appears to solve both problems, being more than strong enough and very good at storing hydrogen and helium. So a civilization might just be enjoying huge amounts of gold or uranium or whatever being returned to their world, and otherwise have no orbital presence because the clouds of debris just make it impractical to have stations or manned ships being built and loaded there. This notion of self-sustaining junk could go further too, as civilizations constantly rising and falling out of worlds could conceivably be building back up into space only to get crashed by a Kessler Syndrome event or something parallel, like inevitable orbital weapon deployment. A few centuries later, they get their civilization glued back together and start launching ships and hunting through the ruins of various old space stations and habitats, and eventually crash again, and so on. This is also very plausible for a full-on K2 Dyson Swarm civilization as well, with the system undergoing periodic cascade collisions and disruptions, and lots of big megastructures left dead but repairable. Many habitats survive, but the debris kills trade and disrupts communication and power collection. They cannot get enough sunlight because their thin and fragile solar collectors get trashed by debris, and it results in a literal dark age. We mostly focused on the idea of being stuck on your homeworld, but home systems works too. For that matter, there's often concern about how long artificial biospheres and ecologies can last on space stations that amount to being a small island, that left alone without trade between them or the homeworld, various habitats would undergo extinctions, possibly all the way down to being lifeless, but probably just to the most simple microbes and such, absent big critters, some very simple biome. I don't think it likely because of how many methods a civilization could counter such die-offs with, but one might imagine chaotic periods in a Dyson swarm causing such die-offs and leaving only scattered pockets of civilization on the homeworld and more isolated and self-sustained habitats, from which the pre-built and mostly intact Dyson swarm needed repollinating from every 10,000 years or such. It is a good reminder that there may be all sorts of hurdles and roadblocks, technological or psychological, to colonizing space that we haven't even encountered yet. We won't really know how clear the sailing is once we launch into space until we have actually made it to those new shores and established long-lasting new communities on them that grow big enough to launch more colonies and choose to do so. Until then, we just assume a lack of known obstacles means there are none. Those might tend to build up with each successive failure too, like you might try to head back out to space in the 40th century AD, only to find out all the very easy asteroid prospects have already been mined, and the mutated descendants of the robots you used for that, while nowhere near human intelligent, still represent a large-scale and dangerous threat to those 40th century ships. Or mutant human miners for that matter, as you might have a million asteroid mines, each with its own enclosed cylinder habitat, all left in isolation for centuries of biological and cultural mutation. Now, while the cyclic civilization collapse notion is very popular in sci-fi, most wonderfully discussed in Niven and Pournelle's novel The Mote in God's Eye, I feel obliged to say that such cycles are mostly poetic, and often in regard to collapsed civilizations that never actually collapse, but which still would only matter if the whole planet had collapsed and not managed to leave records of why. We explored this more in our episode Cyclic Apocalypses. Now, on that subject, a very common suggestion for worlds getting trapped is that if we did burn out in some nuclear war or megaplague that took our descendants centuries to dig out from, then they would have to try to repeat what we did, but with smaller amounts of available resources. On the one hand, yes, you are going to exhaust pockets of easily mined fissile materials like uranium. On the other hand, no, you won't exhaust supplies of iron or aluminum. They make up a sizable percentage of Earth's surface, and while dense pockets of ore might be gone, they mostly just reassemble themselves into other things. A big steel skyscraper is a perfectly good mine for steel a millennia later. Landfills and graveyards become the new places to get mineral wealth from. The Dying Earth genre of science fiction often shows us this, indeed in one of the best book series from that genre, The Book of the New Sun. The author's legendary knack for slipping things in you don't notice to future reads has the protagonist encountering miners on his travel, only for the reader to realize later that they are grave robbers and the concepts have become synonymous. You will not have exhausted all your fissile materials, there's just too much uranium and thorium lying around, and I doubt you will have managed to reassemble your civilization enough to use them without also having rediscovered the concept of a breeder reactor. Then we are talking about millions of years of supply, though to be fair, the planet is expected to live billions of years. My personal hunch would be that any cyclic drop in civilizations would have a period on recovery directly tied to their population regrowth, as they would probably be able to rediscover knowledge from ruins without any real effort. And even absent a diagram of a nuclear reactor or a single text on nuclear theory, simply knowing your ancestors had such a thing would tend to expedite rediscovery. Plus, you would have examples to engineer off of, rebuild reactors tough, so their ruins would still be around for a very long time. Possibly a plague that made people dumber and required 100 generations to rebreed potential scientists and inventors might have this effect. Or some long-lasting anti-tech culture burning books, but otherwise knowledge should be lost minimally and easily rediscovered. Now, usually folks focus on fossil fuels as the missing quantity during a second cycle or third or beyond. That's legitimate, but only to a point, and not simply in that many millions of years later these might be refreshed. Ethanol is ancient. As a reminder, it is simply the chemical name for alcohol, and it is easy to make as our ancestors found. It is unlikely any civilization, no matter how crushed down, is going to forget the antiseptic properties of booze, and I really have difficulty picturing a dystopian ruin of civilization where alcohol was not considered a valued commodity. You probably have to be a pretty determined teetotaler not to see a mushroom cloud rising and not want a stiff drink. And for your descendants running around the wrecked remains of your civilization, catching rats to eat, I'd imagine those taste better with moonshine. Now, alcohol's effect on humans might not be pertinent to aliens with different biologies, and thus might not be easily invented and kept, but parallels might exist and other things burn besides booze anyway, like wood. Other than that, we may assume they know how to make ethanol, that they have several million rusting ruins of combustion engines to remind them why it is handy as a fuel, and the thing about a half-wrecked planet is that there's probably lots of growing space per person, especially for any crop you won't be personally eating and need to worry about toxins, heavy metals, or radioisotopes getting into. Corn may be a very edible ethanol feedstock, but there's tons of other crops that can grow in absolutely dreadful soil that are medium-decent feedstocks, not to mention options like oceanic algae. And we've got a whole planet and only a few million survivors, you really have no problem retooling for an ethanol economy, or a solar one for that matter, if for some reason the soil is ultra dead. That's common to show in post-apocalyptic settings after the bomb, but there's nothing about nukes that cause soil to be dead for protracted times. It's just artistic license. And critically, they already know it's possible to do ethanol, nuclear, and solar, and should be able to get at least one working, honestly all three. They don't have to reinvent the wheel, they see semi-intact bits of them everywhere, and while I tend to think of large populations as a boon, a recovering civilization with a low population but tons of modern technology is quite capable of saying, hey, we can only support 1 billion people on this planet, wrecked as it is, and needing half the land for fuel production. And 1 billion people is more than enough to support modern technology and infrastructure. Probably you only need 10 million if you've already got the tech and need only minor innovation. Now, even that's probably high, but beneath that I think things might get a bit dicey, especially given how many technological edges have to do with massive scales to be advantageous, like trains for freight. One problem though is that ethanol isn't very energy dense, thus it isn't great for planes, let alone rockets. However, while we like kerosene as a rocket fuel, hydrogen is actually better overall, and no civilization is likely to exist where there is a hydrogen shortage. Water can be broken down for its hydrogen as long as you have an electric supply, as we were discussing last week in the future of solar power. Using your peak solar and summer noontime conditions to make hydrogen or hydrocarbon fuels is one possible pathway solar technology might open, and would be available to such civilizations too. Now, in other cases where life evolved on a world that's a clone of Earth but just doesn't have these resources, maybe their world is 1 billion years older and their supplies of radioactive isotopes is much lower. Maybe they didn't have fossil fuels because they formed, but their world is more tectonically active, and pockets tended to spill out and be lost. Indeed, a world with more tectonic activity has plenty of other hurdles in creating civilizations, as does one with very little such activity, since their geological cycles bringing new land and metals and minerals to the surface would be hampered. Earth may occupy a very narrow window tectonically, a geological Goldilocks zone. This one is a bit harder to justify because internal combustion engines would just tend to be a technology you would expect to see develop someplace a civilization was already pretty close to agriculturally maxed out. Indeed, part of the attraction of coal as a fuel back in the day was that it didn't require devoting any precious wood or edible biomaterials to burn. When you're a ruined civilization of a fraction your former number, space is not at a premium. When you're already cultivating every acre, devoting lots of your land to growing biofuels means you need to lower your population, and it's harder for me to imagine many civilizations being willing and able to do that in order to have cars. Maybe for horses though. We usually say a critter like a horse or a cow needs about an acre of pasture, though you can do way better by growing a crop on that field than feeding that crop to the critter instead, even if that crop is hay. Biofuel tends to be in the low hundreds of gallons per acre, varying wildly by crop and location, and without going into depth, my educated guess would be that there would be a strong advantage in doing biofuels for tractors and freight over dray animals like horses and oxen. So I think even on such worlds you would still see that full advancement on engine technology. It might be slower, but centuries are nothing in the grand scheme of the galaxy, and there's no clock running in regards to emptying fossil fuel reserves or greenhouse gas issues. Technologies like computers and aeronautics are unrelated to fuel, beyond simply benefiting from the strength energy abundance lends a civilization. There are other possible shortages too though, phosphorus being a potentially huge one, as we discussed in our episode on that, so we should not rule out a lot of civilizations lagging because of such things. The issue here is that I'm not sure space colonization needs a takeoff velocity. You can't get an airplane in the air until you hit a certain speed, and if you run out of fuel or runway first, it never gets off the ground, but I'm not seeing that analogy applying to technology as well. A civilization that makes minimal improvements over the centuries might need 1,000,000 years to get to space, but they have got it unless they self-destruct. Which of course they might, and if it does turn out that there are events that amount to half-lives on developed civilizations, like a 50% chance of nuclear war per millennia, or a 10% chance per decade of someone releasing an artificial super pandemic, then a civilization cannot twiddle its thumbs getting to space. And that does seem decently probable in some sort of grand galactic actuarial table, that left on a single world long enough, some sort of doomsday event will be engineered beyond a certain technological point. In the absence of such things though, they should have plenty of time. If the cataclysms are small odds per century, or not severe enough to kill folks off so that they can record the problem and pass on to future generations after recovery, then the odds will drop off as they prepare to deal with it in the future. Otherwise, most things which slow you down getting into space are not insurmountable given time, and thus should be surmounted. Let's discuss some of those now. In Douglas Adams' epic Hitchhiker's Guide to the Galaxy series, we encounter a planet called Cricket, where the inhabitants live in a dust cloud around their world that hid all the stars. Once that cloud was penetrated and they saw the rest of the universe, they turned genocidal toward it. But critically, much like my earlier example of a star in the middle of a cosmic void, while their interest in space and even technology might be very hampered by an ignorance of astronomy, they would still presumably invent radio at some point and suddenly see that universe. We can definitely imagine scenarios where wars might have that dust layer obscuring their vision too. Moreover, wars with thick atmospheres have this same potential problem. Worse for them, they are likely to be wars with more gravity than Earth, and more gravity plus a thicker atmosphere to escape through makes that initial effort into space a much bigger hurdle. High gravity worlds and spaceflight don't seem to mix well, and this gets worse when one contemplates that there would seem to be a disproportionate rate increase of oceans and atmosphere volumes with an increase in planet mass or surface gravity. We'll be taking a look at super-Earths next week and we'll explain that in more detail there, but for today's purpose we can imagine worlds with more gravity and thicker atmospheres, ones further obscuring the stars as things of interest to a rising civilization, having a harder time getting into space. Indeed, they might have a lot less land to build launch pads or cities on, with more water on such a world. Fundamentally though, even worlds with twice Earth's orbital velocity and escape velocity can be escaped from by chemical rockets. And that's as high as those get on any plausible scenario for a rocky planet with water and air. And even past that, our Upward Bound series here on SFIA catalogs tons of different ways to get around the rocket equation and limitations of chemical rocket fuels. It might take them a few extra centuries to develop useful spacecraft, but again, what is a century? Admittedly possibly a lot if the Doomsday half issue is in play, but otherwise not, and such worlds have no limitations on normal aircraft, so much aerospace technology would still be developed. Truth be told, that concern about planets being covered almost entirely in oceans, or even entirely in oceans, is a bigger restriction. Life-developing technology on an entirely water-covered planet is potentially a hurdle unlikely to ever be broken. See our episode about the hurdles of technology without fire for details. There may be a very narrow window of conditions that allow a planet to be at just the right mass and temperature to have significant amounts of land and sea and atmosphere, without it all evaporating away on lower gravity planets before intelligence arises, and also without every inch of surface being covered in water and ice. Beyond that though, I would not say gravity was a strong bar to spaceflight on bigger planets, with some big exceptions, some very big exceptions. In his classic novel Dragon's Egg, physicist Robert L. Forward proposes the possibility of life arising on the surface of a neutron star, where gravity is 67 billion times stronger than here on Earth. Now, nothing running on biochemistry is emerging on life on a neutron star. There's not going to be any fossil fuels there, so it does not matter that no chemical rocket is ever getting you off a neutron star's surface if life does emerge on one somehow. A neutron star packs nearly 1,000,000 times Earth's mass into a volume about 20 kilometers across. And even light can't pass near one without being heavily bent, as they have escape velocities of about 1/3 to 1/2 of light speed. Only antimatter offers a rocket fuel that could escape one, though we shouldn't rule out that a life form somehow evolving at the nuclear scale of neutron stars might have access to that substance, potentially even naturally. But outside of nature, such deep gravity wells are an option, as worlds with virtually no gravity well where spaceflight should be easy might turn out not to be. I keep mentioning cyclic civilizations, and it is possible to imagine primitive civilizations existing inside giant space habitats, like O'Neill or McKendree cylinders, without even knowing there was a universe outside. That's a common theme for science fiction about using such space habitats as spaceship, generation ships, or arcs, and indeed is explored as an idea in the twin series to Gene Wolfe's Book of the New Sun, the Book of the Long Sun. Folks living in giant spaceships and not realizing there is a universe outside or beneath their feet in a rotating habitat drum is a fun idea to play with, but also a plausible one. Imagine a group akin to the Amish who are often fine with the existence of technology but do not want it in their daily life, and commissioned a large solar space habitat with a benign AI to maintain it. 100 generations later they forgot what it is, and 100 after that they forgot they disliked technology and pursue it again. Not easy to develop technology on a world that's artificial and which was built to hide its technology too. Hard to see an outside universe when outside is down and your world is a giant cylinder or egg. And there may be whole galaxies worth of civilizations all around you, possibly peopled by nigh immortal folks or superintelligences who were alive when your world was made, but consider it illegal or rude to poke inside when you asked them not to when you built it. I mentioned giant gravity wells as a thing we might build though, and one alternative for artificial worlds is building big spherical shell worlds, and we have contemplated building those around juggernauts like neutron stars and black holes before. Huge hollow worlds whose surface looks like Earth, but with a neutron star or black hole in its center for gravity and power generation. We call these mega-Earths, things which not only dwarf normal planets but dwarf most stars, and which would have surface areas 1,000,000 times bigger than Earth's. On such worlds, the surface gravity is the same as on Earth, or the species' homeworld, as they simply build the shell that far from the central mass. However, the escape velocity of such an artificial behemoth is vastly higher. 1,000,000 times Earth's mass with 1,000,000 times our surface area would have a radius 1,000 times Earth's and an escape velocity the square root of 1,000 higher, or 32 times our escape velocity. That is not plausibly within the realm of a chemical rocket, but it is within the realm of various active support structures we have discussed, and whose technology they must have mastered to have built that shell in the first place, though future generations might have lost that knowledge, I suppose. Still, much like with the Niven Ring world, it is hard to imagine a structure 1,000,000 times Earth living area not being able to solve the problem of spaceflight with presumably 1,000,000 times as many people to do their science. Now of course that is another way a species could be bound to their world if their brain architecture just didn't produce those outlier science minds. We don't know that intelligence like ours evolves much, as we discussed in our Rare Intelligence episode, but even if it does, our world is not technological because the average IQ is 100. It's technological because of that tiny fraction who are 150 plus, which is less than 1%. But if your brain architecture makes that degree of outlier much rarer, that might basically leave an entire world of very smart folks, but none who were STEM geniuses. We should not make many assumptions about how brains are structured on other worlds. They may not have any variation in IQ between people, or range a lot tighter than we have, like our ranges for height or visual spectrum range. Or their exceptionalism might be in other areas of intelligence than what result in rocket science, or worlds of master poets that when it comes to science just don't nose it. They may also never leave their world in favor of importing material by robot explorers, and it is worth noting you can build way bigger than even mega-Earths if you want. Many galaxies have giant black holes massing millions of stars in their central region, and artificial worlds in this class, shells or even multiple layers of concentric shells, were suggested by Paul Birch for these galactic core worlds. These could potentially be built even up to 1 trillion solar masses. And in that Mega-Earths episode I coined the term Birch Planet for those mega-Earths in this millions to 1 trillion solar mass range. I'm rather glad to see the term seems to have caught on and spread inside sci-fi circles, as Paul Birch is horribly under-recognized for his ideas. What's neat about these titanic galaxies in a planet is that they might contain many quadrillions of times the living area Earth has, especially the kind we might build around late universe juggernaut black holes that ate their whole galaxy up. On those, time would run a good deal slower, especially on the lowest levels closer to the black hole in the basement. Unfortunately, these worlds are easier to get to than to leave, and civilizations opting to live on one are making fairly permanent travel arrangements, because even the smaller Birch planets of just a few million solar masses would have 1 trillion times the mass Earth does, 1 million times its radius, and 1,000 times its escape velocity, 11,000 kilometers per second, or almost 4% light speed. For the mass of our whole galaxy, that would be more like 40% light speed, in the zone of those hypothetical civilizations living on neutron star surfaces in Dragon's Egg. Easy to reach, nigh impossible to leave. Mass drivers on a scale as big to those we contemplate as Birch planets are to our own world might be needed to make flight off such a world economically viable. Now, I mentioned how black holes of many billions of solar masses might become common in the late universe, and it is worth noting that all our galaxies are slowly flying apart. Those galaxies close enough to stay together will eventually merge over the next 100 billion years, as in truth they have been doing for billions already. Our galaxy is quite the cannibal, while all those galaxies which aren't close enough will have disappeared over the cosmological event horizon. Star formation will be about as common and plentiful as now. Even then, it doesn't really start to seriously dip till well after the trillion-year mark. If we were in some galaxy that was the leftover of such mergers, and which the first civilizations only arise then they could look around 100 billion light years and more and see no other galaxies. They might feel pretty isolated and assume that was all the universe was, one lone island of 1 trillion stars, not even 1 million light years across, surrounded by billions of light years of nothing. Of course, that's still 1 trillion stars. But between galaxies there are a lot of stars too, ones ejected into intergalactic space and which might not have any neighboring stars for thousands of light years, currently. They wouldn't really see stars, they'd see the hazy blur of a galaxy and maybe notice individual stars after they invented really nice binoculars. Still, we could imagine them eventually realizing there was a galaxy nearby, and other stars even nearer, and deciding to send generation ships off to claim those. They would have a much higher hurdle than we do to contemplate interstellar colonization, but I suspect they would still try. However, those intergalactic ejects can find themselves lost forever, one lone star not gravitationally bound to neighboring galaxies, and a red dwarf with a planet might easily find itself stuck 1 trillion light years from its nearest neighbor before it ran out of fuel, with life arising on it and reaching intelligence long after any real trace of other stars and galaxies was erased. They might never realize there had been a bigger universe, and travel to it is out of the question at that point. Of course, if such worlds exist, they do so only in a future sense, a thing to arise 1 trillion years from now. Let us imagine one other case though for the day. One very popular solution to the Fermi paradox is that we might be in a zoo or quarantine, where we simply don't know about the galaxy around us. In practice, this approach is better done by something like an obscuring layer around that world to hide the real universe, as was the case for that world of cricket I mentioned earlier. Someone hid the universe from them originally. This can be taken to many degrees, like placing a minefield around a world that seemed natural, or even placing an actual black shell around a world or an entire solar system to hide the outside galaxy. Indeed, you might put little fake suns on that sphere, like some of our ancestors envisioned might really be the case for the celestial sphere. Or you might upload their minds and place them in a simulated world. Or, if your technology permits it, you might place them in a pocket universe you created. You might even be kind and give them some artificial giant world, McKendree cylinder, ring world, rung world, or a mega-Earth all their own, with another layer or black shell above in their sky. A very nice zoo, but a zoo nonetheless. Those are certainly good ways to keep a civilization bound to its homeworld, or its new world anyway, if that's your goal, quarantine or containment or entertainment. I don't think such options offer a very good solution to the Fermi paradox, unless we are the ones in such a zoo, of course. One last thought to close on though. I began the episode by calling on everyone to contemplate civilizations that realized how big the universe was, then realized it was denied to them, and it reminded me of a scene from Isaac Asimov's novel The End of Eternity, my favorite standalone novel by him, and the best time travel novel since H.G. Wells' Time Machine. In that scene, we see people reacting to the constant trial and failure of their civilization of thousands of years to get to space and establish themselves, instead each time retreating. Trips to the distant future show humanity simply dying off because by the time they finally got out into the galaxy, every planet was taken by aliens. Not hostile, but already occupying the real estate, and they just settle down onto Earth and give up, and a million years later, Earth is empty. It is a depressing reality to face, but if a civilization can fall apart or die off from seeing themselves trapped to one world, or if they are prone to blowing themselves up, or if they just can't be unified to a common goal because they only have themselves and their world to fight for or over, it's not too hard to imagine civilizations on imprisoned planets might be short-lived ones. I don't think it's likely, but that was Enrico Fermi's original solution to the Fermi paradox. Intelligent life might be common, but it's all trapped on its homeworld or system till it kills itself off. The troubling thing is that it may turn out that space travel is harder than we often think, and we won't know till we have done it, but it might be we and every alien world just find space colonization a path of constant setbacks and impractical hurdles, of demoralizing defeats, and even though there's no dangerous debris around our world confining us, no bars on our prison door, we end up every bit as imprisoned and doomed to this one world, and that not for long. So we are a little over a month into our new year, and chances are pretty good you have some New Year's resolutions you've made, and often by February a lot of those are already on the scrap heap, or close to it, maybe yours or maybe a friend or loved one. And a lot of times that's not because the goal is too hard, so much as remembering to work on it each day is tricky. A lot of times the difference between success or failure on those or other life goals is just getting those reminders until the habit gets established, and that's where our fabulous new sponsor, Fabulous, can help out. There is very real behavioral science behind how we develop habits and what sort of hurdles or assistance can stop or help you from forming new habits. And Fabulous has built their app around the science for building healthy habits that stick. As an example, we all hear about the importance of drinking enough water. It is probably one of the most critical and easy life changes to help with your health, physical and mental. But most folks just can't get into the habit of drinking enough. I never did establish that habit until I was in the army and getting ready to deploy to a desert, and we had reminders all over the place about its importance. It was very difficult for most of us to get into that habit even then, and so I greatly appreciated that the first habit to work on that their app suggested to me to get used to the program was water drinking, a simple but vital habit. So Fabulous focuses initially on simple and easy habits and recommends many to you, but fundamentally it is about helping you achieve your goals without any gimmicks. It just focuses on setting up reminders and coaching. It's 100% personalized and lets you go at your own pace, and it will help you get back on the horse if you need to. You're investing in yourself, and that can be a hit and miss and rocky process as you build new and better habits, turn desired healthy behaviors into habits, or work toward new personal goals. It doesn't just tell you to eat a healthy breakfast, it walks you through examples of them and scientific explanations of why that's a good idea, and helps you incorporate what you love and what's good for you into your daily routine. Only you can achieve your personal goals and change your habits, but Fabulous has programs to help you reach your objectives, develop your motivation, and discover wellness practices to help you become more fabulous. Start building your ideal daily routine. The first 100 people who click on the link will get 25% off a Fabulous subscription. So this will wrap us up for another Sci-Fi Sunday, and we'll be back again next month for a look at synthetic life forms, what those are and what it might be like to be one, drawing on inspiration from many science fiction stories, examining the concept from different angles. Before then though, we have plenty of our regular Thursday episodes coming up, starting this Thursday with a look at super-Earths, both in terms of evolving on them and our options for colonizing them. And as we mentioned today, there's a chance those might be entirely oceanic, and 2 weeks from now we will examine some megastructures and space habitats built with marine habitation in mind, including a new ultra-large megastructure option we have not examined before. Now, such megastructures take huge amounts of mass to build, and sometimes more than an entire solar system might contain of a certain element, so we'll go into March looking at nuclear transmutation options for civilizations that don't want to wait on supernovae to get more materials. And of course, such megastructures often assume lifespans similar to the planets they emulate, so on March 10th we will take a look at how you could build a machine designed to last 1,000,000 years. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.